Hello, this is Andrew Clevenger from the University of West Florida's Sevil Research Group, and today I'll be presenting our paper, Analysis of Post-Disaster Damage Detection Using Aerial Footage from UWF Campus After Hurricane Sally. Working with me on this study is Mr. Lawanda and Dr. Sevil, as well as Mr. Mahayari from the Florida Institute for Human and Machine Cognition. We'll start with an introduction to this study and the motivation behind it. Then I'll go over the data used for our methods. There are two different methods we use, the convolutional neural network and Cascade classifier. Then we'll go over the results of both of those, and finally give some conclusions and some future works for the study. Okay, so this study is all about object detection. And what is object detection? It's essentially a method for localizing objects within an image. So we're going to input an image into an object detection model, and we're going to get out a few things. We're going to get a list of bounding boxes, which tell us where the object is within the image frame. For each box, we're going to get a predicted class, and we're also going to get a list of probabilities that that object is each possible class. What is it used for? It's typically used to provide information to other algorithms. The most common example would be for self-driving, to say locate a stop sign. Because this is a machine learning method, we can use training data to teach our models to identify whatever it is we want them to identify. So in this study, we attempt to use that to identify roof damage in videos captured by an overhead drone camera. So as I said earlier, we are comparing the effectiveness of two different object detection methods. The first will be the convolutional neural network, and the second will be the Cascade classifier. For the convolutional neural network, we'll be using the faster RCNN with Inception ResNet v2 model, and for the Cascade classifier, it'll be the OpenCV HAR-like feature Cascade classifier. Now onto our data. For the training data, we use the ISBDA dataset, which is a hurricane damage dataset captured by overhead drones. This dataset comes with annotations for damage segmentation, damage bounding boxes, and house bounding boxes, but we did not use any of these annotations and instead re-annotated images ourselves. For the testing data, we captured footage of the University of West Florida campus buildings with our own drone camera. So our first method for object detection uses a convolutional neural network model. So what is a convolutional neural network? It's essentially a standard neural network which has been adapted to process images through convolution. What is convolution? So convolution takes an input image, such as this one. It takes each section of that image and multiplies it by a convolutional filter or kernel, which is just a small matrix of specifically selected values designed to draw out certain object features. So this multiplication produces a value which will be output into the feature map. And each section of this image is multiplied by this kernel to fill out this feature map, which for example could be object edges, which will be useful for determining where an object is located in the image. This process of convolution is repeated many times for each image using different convolutional filters to produce many feature maps. So here is an example of a pass through a convolutional neural network. You can see at the top is going to be the output of our first convolution, which is many feature maps. And then we pass through layers which are designed to reduce the size of the input, to normalize the feature maps so that the network can generalize, and to further strengthen the features. And at the end, we wind up with very small feature maps, but with dense information about the objects. The specific convolutional neural network model we used was the TensorFlow implementation of faster RCNN Inception ResNet v2 for 640 by 640 pixel images. And this model came pre-trained on the COCO 2017 dataset. Pre-training is a common method which will typically improve the results of a retraining an object detection model. How does faster RCNN compare to other object detection methods? Well, it's quite slow for processing, but it has good accuracy. We can see a diagram of how the model works at the bottom. We take our image, we input it into the convolutional layers, which will output the feature maps. These feature maps are input into the region proposal network, and for each spatial location in those feature maps, we do an objectness classification, which tells the probability of an object being at the location, and we do a bounding box regression, which tries to place a bounding box around the object. So these bounding boxes are output in the form of region proposals or regions of interest, and we can lay those on our feature map. Now, to refine those, we do region of interest pooling, and that's going to give us our final output multi-class classification, which assigns a class to the object, and bounding box regression again, which will refine the bounds of the box around the object. Okay, so on to our second method. We have Cascade classifiers. Now, Cascade classifiers use HAR feature kernels, which are similar to the convolutional kernels, to detect HAR-like rectangular features within input images. Now, regions where we detect features in the image are going to be passed to the second classifier, which is going to scan the same regions and test more features. And if it passes the feature checks again, it's going to be passed again to the next classifier and the next classifier until we finally get to the end where the actual predictions are made. So the first classifier is going to be very lenient and not test many features. It's going to make many predictions, and many of those will be false positive predictions. But the idea is that as it passes through more and more classifiers, the false positives will be filtered out, and hopefully the real predictions will be kept. The specific implementation of Cascade classifier we used in this study will be the IPCV Cascade classifier. Okay, on the left we can see the HAR-like featured kernels, which are essentially just matrices with binary values, and those can be assembled in any rectangular format. And on the right we can see how those kernels are applied to our image. We're going to lay each kernel on top of an image region, and we have two separate parts of the kernel, the shaded and the unshaded region. So each one of those regions is going to be summed, and then the unshaded region sum is subtracted from the shaded region sum, and that's going to give us a single value. And if that value passes our threshold, then this region will be passed for that feature check. And if it doesn't pass, it is discarded completely. Now on to the results for both of these methods. We chose two particular videos of our overhead drone recordings of damaged UniVF buildings to test their performance, and we chose two different kinds of metrics to record. The first was the average detection rate as well as false positive rate, and the second was a precision and recall variation by frame chart. We also provide visual examples of both detectors' performance. Before we get to the actual results, I do want to quickly go over what is a precursor to most object detection metrics, the intersection over union score. So if we look at the bottom example, we can see we have two different boxes, the ground truth box and the prediction box. We're going to take the intersection area of those two boxes, and we're going to take the union area of those two boxes, and we're going to divide the intersection area by the union area. That's going to give us our intersection over union score. Now for our study, we chose that a intersection over union of 50% or greater would be a true positive detection, and anything less than 50% would be a false positive detection. Now, with that in mind, we can say that the detection rate is equal to the number of true positives divided by the number of ground truth instances, and the false positive count is equal to the number of false positives divided by the number of image frames analyzed. The top two tables show the CNN results, and the bottom two tables show the Cascade classifier results. And we also selected particular sections of both of these videos where the classifiers did particularly well, and we believe that shows the potential of these two classifiers, while the charts on the left show the actual results for extended periods of video. Alright, and now I'll just read off these results. So for the CNN and the entire video, the average detection rate for Argo Hall was 55%, and for Martin Hall it was 48%. And the average number of false positive detections was 0.15 in the Argo Hall video and 0.29 in the Martin Hall video. Now for the selected sections, the average detection rate for the Argo Hall video was 85%, and for the Martin Hall video it was 88%. For the average number of false positive detections in the Argo Hall video, it was 0, and in the Martin Hall video it was 0.08. On to the Cascade classifier. The average detection rate for Argo Hall video was 41%, and for the Martin Hall video it was 41% as well. The average number of false positive detections for the Argo Hall video was 0.13, and for the Martin Hall video it was 0.04. Now for the selected sections of Cascade classifier, the average detection rate for the Argo Hall video was 48%, and the Martin Hall video was 55%. Now the average number of false positive detections for the Argo Hall video was 0.06, and for the Martin Hall video it was 0. On to the graphical results. We can see the precision is calculated as the number of true positives divided by the number of all predictions made, and the recall is calculated as the number of true positives divided by the number of ground truth annotations. So you can think of precision as a measure of how good are the predictions we're making, and recall as a measure of are we making all the predictions we want to be making. And these are the graphs for the CNN. Note that these are precision recall variation by frame and not precision recall plots in the traditional sense. On the left we can see the Argo Hall graph. On the right we can see the Martin Hall graph. You'll notice in these graphs that the recall is typically quite a bit lower than the precision, which means a lot of our instances aren't being detected at all. So we'd like our detector to make more predictions going forward. And in the Cascade classifier graphs, you'll notice a similar issue to the CNN detector. The precision for the Cascade classifier was very good a lot of the time, especially in our Argo Hall video, but the recall gets very low. We have many missed detections with this detector. Lastly, for the results, we will just go over the visual examples. And these are for the CNN model. You can see we have the detection boxes as well as the pixel coordinates. And I'll just slowly scroll through these. You'll notice that the main issue in these detections is missed detections rather than bad detections. Although we do have some false positives, the main issue is that there are a lot of missed detections. And for the Cascade classifier, the issues with this were essentially the same, where the detections made were fairly good detections. There's just a lot of missed detections. Okay, conclusions and future works for this study. We found that the CNN model had a much better detection rate than the Cascade classifier, but its detection was very slow. The Cascade classifier predicted less false positives very quickly. We believe if we had more training data of a high quality, we probably could have made both of these models significantly better at making detections and filtering out false positives. And we also believe if we had better testing data, we could more readily test these models, as we had two classes of medium and heavy damage, which weren't really tested at all in this study. That will be all for this presentation. Thank you for watching. If you have any questions, you can contact Dr. Sevil at the links below.